we're going to look at a few example problems illustrating how to calculate the pH of a buffer and how to calculate the pH of a buffer after an acid or base has been added to the buffer. In the first question here, we're just going to look at a buffer that's been made. It says calculate the pH of the buffer. The result from mixing 60 milliliters of 0.25 molar HCHO2 and 15 milliliters of 0.5 molar of its conjugate base, and we're given the Ka for the acid. So we have already the amounts of both the conjugate acid-base pair, and we're going to use the buffer equation, which remember is really just the Ka equation rearranged. So the hydronium concentration is equal to the Ka of the acid times the concentration of the acid over the concentration of its conjugate base. And we've got to figure out the concentrations of the acid and conjugate base once they are mixed. And so the concentration of the acid is moles per liter. To figure out the moles before it was mixed, moles are molarity times volume in liters, which would be 0.060. So that would be the moles of HA, and they have divided by the total volume of the solution, which should be 60 milliliters plus 15 milliliters once it's mixed together, so 0.075 liters. We're going to do the same sort of thing to figure out the concentration of A minus once the two things are mixed together to make a buffer. So to figure out the moles of the conjugate base, we'll take the molarity, 0.5, times the volume, 0.015, divided by the total volume once everything is mixed together. So it'll be moles per liter. So I'm going to plug those two things into my calculator and get a numerical result for the concentration. The concentration of the acid is 0.2 molar, and the concentration of its conjugate base is 0.1 molar. Therefore, coming back to the buffer equation, just the rearranged Ka equation, the Ka is 1.8 times 10 to the negative fourth. The concentration of the acid is 0.2. The concentration of its conjugate base is 0.1. So the hydronium concentration for this buffer is 0.00036 molar. And to get the pH, I'm going to do the negative log of that. And so I've determined that the pH will be 3.44. Again, we're going to look at a buffer. This time, in addition to figuring out the original pH of the buffer, we're also going to look at how the buffer would respond to adding a strong base or a strong acid. So first, looking at the buffer, this time we have something that is basic, NH3 and NH4Cl, and we're given the Kb. So instead of using the equation that we did on the previous one, we're going to use the Kb expression rearranged. So the hydroxide concentration is going to be equal to the Kb times the concentration of the base, which would be NH3 in this case, divided by the concentration of the base's conjugate acid. And we're told that this is a 1 liter solution, and it's already mixed. The acid-base pair already mixed, so we don't need to figure out new concentrations like we did on the previous one. We can just figure out that the hydroxide concentration is equal to the Kb times the concentration of the base, which is 0.5, over the concentration of its conjugate acid, which is 0.2. So the hydroxide concentration, when I plug that in, is 0.000045 molar. So the pOH is the negative log of that number, which is 4.34, and take that and subtract it from 14 to get the pH, which is 9.65. So this buffer is going to be a buffer that operates more in the base pH range at 9.65. Next, this is what's the pH of the buffer after adding 0.010 moles of solid sodium hydroxide? Well, first we got to think about the fact that adding sodium hydroxide basically means we're adding hydroxide. And we got to think about which half of the buffer is going to work with that. Well, if this is a base, the acid part of the buffer is going to work to neutralize it. So we'll have a neutralization reaction here between the hydroxide and the NH4 to make water and NH3. Then if we want to figure out the final pH, we need to actually go through and do a BCA table and figure out what's left after this neutralization reaction happens. So we added 0.010 moles of hydroxide. The NH4 moles we could get from its concentration. The concentration of NH4 is 0.02 molar, and we've got 1 liter of it, so that means we'll have 0.02 or 0.2 moles. And this is what it should be. The thing you're adding to the buffer, there should be much less moles than there is of the acid in the buffer to neutralize it. We do have some NH3. Keep that in mind. We have 0.50 moles of NH3 because the buffer already has both the conjugate acid and conjugate base pair. So we have no hydroxide left. That's the point. The buffer's trying to get rid of that. We have 0.19 moles of NH4. We have made some water, which we're not going to really care about, and we have 0.51 moles of NH3 now. I'm going to assume that the volume is still essentially 1 liter that we, and it said we added solid NaOH, so that's not going to change the volume much. So we will calculate the new pH again using the buffer equation. But now our concentrations are 0.51 over 0.19. But then we're just kind of following the same steps we did in the previous calculation. The hydroxide concentration is 4.83 times 10 to the negative fifth. So the negative log of that gives us the pOH, which is 4. And the pH is 9.68. I must have not written all the decimals for the pOH when I put it in my calculator. So notice the buffer did its job and the pH really only changed very slightly, and it went up because this is a base that was added to it, but it only went up a very, very small amount. So we're going to do the same thing. What's the pH of the buffer after adding hydrochloric acid? So hydrochloric acid is essentially adding H plus to the solution. The basic part of the buffer is what's going to react with this, NH3, and it will neutralize that by making NH4 plus. So we're going to figure out how many moles of everything there is. We've got, and I'm going to go back to assuming we start with the original buffer rather than the buffer after part B. So we have 0.5 moles of NH3, we have 0.2 moles of NH4 plus, and we just added 30 milliliters of 1 molar HCl. Volume times molarity gives moles, so this will be 0.03 moles of hydrogen or hydronium. So we're going to do the BCA table calculations, do the stoichiometry here. We've neutralized all the H plus. We now have 0.47 moles of NH3, and we have 0.23 moles of NH4 plus. Now this time, because the previous time we didn't have to worry about the volume changing because we added solid NaOH. This time the volume did change. We added a solution. So to figure out the concentration of these two things, we need to take into account the fact that the solution, its volume is now 1 liter plus 30 milliliters, so it's 1.03 liters. And this is 0.23 moles over 1.03 liters. And we're trying to figure out the hydroxide concentration, so just like we did on the previous two steps, the hydroxide concentration is equal to the Kb, the same buffer system we're working with. And actually, if you look at here, we realize we didn't have to calculate the concentration, because if we take the base concentration, which is 0.47 divided by 1.03, and the acid 0.23 divided by 1.03, really the concentration or the volume cancels out. But it's good to think of that step because sometimes that will matter. So the hydroxide concentration, I actually didn't write down, but I got that the pOH was 4.43, and so the pH would be 9.56. Notice again, we added an acid, so the pH went down a little bit in comparison to the 9.65, but the buffer did its job and the pH did not change a great deal. We got one more example on the next slide. The last topic is, how do you make a buffer? Like, if you know that you need a certain pH and you need a buffer, how do you go about doing that? So in this first thing to keep in mind is the target pH that you're looking for should be close to the pKa of the acid, so that you get that half equivalence point conditions where you have about the same amount of acid and conjugate base, that conjugate pair. So in this case, we have carbonic acid, we have sodium hydrogen carbonate, and we have sodium carbonate. And it says, what are some ways you can make a buffer with a pH of 10.1? So we got to decide, we got 3 chemicals here, but we should probably only need 2 of them to make a buffer. So we could either do the carbonic acid with the sodium hydrogen carbonate, or we could do the sodium hydrogen carbonate with the sodium carbonate. Notice we've got 2 Ka values here, Ka1 and Ka2. We have 2 values because carbonic acid is a diprotic acid, which means it can give, the first Ka is for giving away the first hydrogen, and the second Ka is for giving away the second hydrogen. So the first thing to decide is which of those 2 Kas is going to get us closer to that pH of 10.1. And remember that pH and pKa can be estimated by looking at the exponent on the 10. So we've got 10 to the 7th, or 10 to the negative 7th, and 10 to the 11th. And of those 2 choices, 10 to the 11th is closer. It's going to get us in the range of that 10.1 pH that we want. That means that because these 2 match, we are going to be looking at making a buffer out of the sodium hydrogen carbonate and the sodium carbonate. So to figure out what we're going to make, think about the buffer equation. In other words, the rearranged Ka expression. That the hydrogen concentration is the Ka times the ratio of the acid and its conjugate base. We need a pH of 10.1. So the hydrogen concentration for that would be 10 to the negative 10.1. The Ka we're looking at is 4.8 times 10 to the negative 11th. And so we're trying to we want to know what the ratio of HA to A minus would be. So if I just divide the 4.8 times 10 to the negative 11th over to the other side, I get that the ratio of HA to A minus should be 1.65 to 1. So that means to make a pH, a buffer with this pH, we need to have 1.65 moles of HA for every 1 mole of A minus. You could do that twice that, you could do 3 times that, but they have to be combined in that ratio. 1.65 moles of acid for every 1 mole of base, so that the buffer starts at that target pH. Now I have a couple of other conceptual questions I want you to think about. What if you didn't have all 3 of those chemicals available? You didn't have these conjugate acid-base pairs available. What if you only had NaHCO3 and we want to make this same buffer? Well, we said we need 1.65 moles of the acid, that would be this, and we need to make some base. we could take this and we could react it with a strong base. Any strong base, really. And do kind of a titration almost, where we start with a whole bunch of extra NaHCO3. We'll do 2.65 moles of it, and we'll add to that 1 mole of hydroxide. What that will do is hydroxide will be our limiting reactant. It's all going to get used up, but then we will make H2O and CO3 minus 2, the other half of our what we need for our buffer. So we will make 1 mole of that. And what that will give us, after the base has been neutralized by the sodium hydrogen carbonate, we will have 1.65 moles of HCO3 minus, and we'll have 1 mole of CO3 2 minus. And notice that, that matches the ratio that we said we needed earlier. So if you just have one of the two pieces of the conjugate acid-base pair, you can generate the other one by basically doing a titration to approximately the half equivalence point. So similar, what if you only had the sodium carbonate? Well, then you could react that sodium carbonate with a strong acid and make it go backwards on the titration curve to the half equivalence point, or close to the half equivalence point. So we could say, all right, I've got some carbonate. I'm going to react it with a strong acid, and we will make HCO3 minus, the thing that we're missing. And we would start with 2.65 moles of this, and we would add 1.65 moles of H plus to it, so that 1.65 moles worth of the carbonate ion is converted into its conjugate acid. And again, that accomplishes the same thing as we did before. We've got 1 mole of carbonate ion for every 1.65 moles of hydrogen carbonate. So the important lesson here is, the first time I learned about buffers, I thought you had to have the conjugate acid and base pair. But you can also have a weak acid and a strong base that converts some of that weak acid, about half of it, into its conjugate base. Or you can have a weak base and then use a strong acid to convert about half of that weak base into its conjugate acid. That's my last calculation example, so now it's time for you to give some a try on your own.